Now we're going to look at some periodic trends in different properties of the elements. So the first one we're going to look at is atomic size. And before we can look at the trends, we have to decide, well, how are we going to define the size of an atom? Because, you know, it's not a solid object and we can't measure it with a ruler. There's a couple of different ways of defining atomic size. One is the non-bonding atomic radius, also known as the van der Waals radius. And so this looks at the element as a solid and says, well, you know, two atoms next to each other, we can measure the distance between the nuclei, and so half the distance there would be the radius of the atom, and that's going to be the size of it. We can also look at a bonding atomic radius or a covalent atomic radius where the two atoms are covalently bonded to each other. And again, looking at half the distance between them. This is generally going to be smaller because, especially with the covalent bonds, they're sharing electrons and it pulls them closer together. So we're going to do something called atomic radius, which is really just an average of the atom size in a whole bunch of different compounds and as an element. And so just a more general term. When we talk about bond length, we can approximate the bond length by adding the atomic radii. So over here, we can use the distance between these two to find the radius of the atom, but we can also estimate that distance by looking at the radius of each atom and adding them together. That works for covalent bonds.
Only covalent?
Yeah. It doesn't work for ionic because when you form ions, the size of the atom changes remarkably. We'll get to that. So this is a graph showing the trends in radius as a function of atomic number. And it kind of looks like a big mess, doesn't it? But what's in red down here, these are the noble gases. And so if we look at those, we see that as you go down the group, those atoms get larger, right? And up here, the alkali metals, lithium, sodium, potassium, rubidium, cesium. Again, as we go down the periodic table, they get larger. And this one makes sense because, you know, radon, is radon on there? No, xenon, 131 grams to helium's 4 grams. You would expect this to be bigger. It weighs a lot more, right? So that's a trend that students don't usually have trouble with. Quantumly, the N is increasing, so we talked about valence electrons now, and the principal energy level where those valence electrons are is getting bigger as we go down here. So this has its valence electrons in the second level, third, fourth, fifth, and sixth. And so the sixth level is further out. And so that would also make the atom larger. What doesn't make as much sense until you understand why is that the atomic radius decreases as you go across a period. So, like going from rubidium to xenon, you might think, well, xenon should be bigger because it weighs more than rubidium, but it's actually significantly smaller. And this is not a hard and fast trend, but it's a general trend that going across gets smaller. So what on earth is going on here? This has to do with shielding and effective nuclear charge. So we've got these multi-electron systems, and we've got electrons being attracted to the nucleus, but also being repelled by each other. And so the outer electrons, the valence electrons, are shielded from the nucleus by the core electrons. And so they don't experience the full charge, which means that they're not pulled in as tightly as we would expect. So this is lithium again. We looked at this before. Positive 3 charge on the nucleus. This has 2 core electrons, that's the 1s2 electrons, and it has 1 valence electrons, the 2s electron. So the 2s is a little further out than the core electrons, and so when it views the nucleus, it is seeing it through these core electrons. I made the analogy better yesterday during class. So now we don't have the bodybuilder putting on a parka or taking it off, okay? So here you've got these core electrons are like other people that are drawn to this person, and they're forming a crowd around them. And so you can't really see them as well, and so then they're not as attractive as you could, see their full physical glory or whatever. And that analogy works really well for penetration, because penetration means that this electrons cloud is able to push in among the crowd in here, and so then they can get a better view. But here,
it's more, so it's, on this type of thing, it's more of its electron activity in a sense, or not necessarily?
well, we're looking at, and basically this comes down to Coulomb's law, which says that the force of attraction between this negative charge and this positive charge depends on the size of the charges, right? So this is a -1 charge. This has a +3 charge, but this electron doesn't get to see the whole +3 charge because there's these other 2 electrons that are sort of shielding it. And so as this electron looks through this inner core cloud, it's got those 2 negative charges and a +3, and so it appears to be a +1 to this electron out here. So then the effective nuclear charge is only +1, and so the electron isn't pulled in as far. Okay? Any questions? Is that making some sense?
So like when we, I think, you're gonna have an example of that. When we go to-
So we can estimate the effective nuclear charge by looking at the actual nuclear charge, number of protons in that nucleus, minus the number of core electrons. Now, valence electrons do contribute to shielding, but not very much, and so we can just conveniently ignore them. So what's the effective nuclear charge of nitrogen and of argon? So let's look at nitrogen. So nitrogen is got 7 protons, right? It's got 7 protons and 7 electrons. If we look at its electron configuration, we would find it to be 1s2, 2s2, 2p5. Nope, that's not right. 2p3, sorry. Yeah, that adds up to 7. So in the second level here, those are the valence electrons. We can also identify the number of valence electrons because it's in group 5A. So it has 5 valence electrons. So these are the valence electrons. Those are the core electrons. So the effective nuclear charge is equal to the charge on the nucleus, which is +7, minus the number of core electrons. So these are the core electrons. And you can calculate the number of core electrons because you take the number of electrons, 7, minus the valence electrons, and that gives you the core electrons. Or you can look at the electron configuration, but people don't tend to like that. So we've got a +7 charge, but we have 2 core electrons, and so those get subtracted because they kind of shield the nucleus, right? And so we end up with a +5 charge. It's the effective charge on the nucleus that the valence electrons see. Because there's 2 electrons in there that are shielding it, right? They're obscuring the charge, and so we don't get as good of a view, Because the charge is less, the force of attraction for these electrons is less. So let's look at argon. How many electrons does argon have? 18. So it's got 18 protons, 18 electrons. How many valence electrons?
Oh, 8.
8 valence electrons because it's in group 8. So the effective nuclear charge here is going to be the plus 18 on the nucleus minus the number of core electrons. So we could figure that out, but we can also just take the number of electrons and subtract the valence electrons, and that'll give us the core electrons. So 18 minus 10 is positive 8. So the elements on the right side of the periodic table experience a higher effective nuclear charge. The force of attraction between the nucleus and the electrons is stronger, which is going to pull the electrons in closer, making the atoms smaller.
So argon was for effective nuclear charge is 8, right?
Yeah.
Okay.
And if you do it, you find that the effective nuclear charge for all of the group 8 is 8. Yeah. So, wrong thing. Here we go. Nope. Okay. So when we're moving down a column, we've got the principal quantum number increasing, which gives us larger orbitals and thus larger atoms. That's the one that we don't have much trouble with. Moving across a period, the effective nuclear charge is increasing, while n is the same. So those valence electrons are in the same principal level, but as you go across the period, the effective nuclear charge is getting bigger and bigger. So the effective nuclear charge is going to pull the electrons in a little bit, and that's why the atoms get smaller as you go across. Let's go back to this one. So here's nitrogen. Oh, that's not a good example. See, this is not perfect, is it? 77, 70, 73, 72, 70. But the general trend is that as you go across, they get smaller. It works for phosphorus and argon. So phosphorus would also have a +5 effective nuclear charge, whereas argon has a +8 effective nuclear charge. And so that pulls the electrons in more tightly. Okay. Now, when you talk about the transition metals, those are the ones that like to violate lots of rules. If we're looking at the columns, they follow the trend. But if we look at the rows going across, then there's very little difference in the sizes. And the reason there is that the valence shell is that S sublevel. It's not those d electrons. And so as you're going across, because what you're adding is core electrons, really the effective nuclear charge for all of the transition metals is roughly the same. And so their charges, their radii don't change much. Okay, so what do you need to be able to do with this? You should be able to answer a question like this. Identify the larger atom in each pair, if possible. So the trend is that as we go across, it gets smaller. As we go down, it gets larger. Or if you want to say, well, going this way, it gets larger. So if we look at tin and iodine. So let's find these guys. There's tin, and here's iodine. Based on periodic trends, which one should be bigger? The tin should be bigger. Because as we come across, they're getting smaller because of the effective nuclear charge. So we would expect tin to be larger. Let's look at germanium and lead. Here's germanium, and here's lead. Which one should be bigger? Lead. As we go down, they get bigger. That's the one that makes sense. So we would expect lead to be bigger. Oh, except that isn't lead, that's PO. Yeah. But if it was lead, lead would be bigger. Oh, where'd you go? Oh, here it is. Okay, so this one's at an angle, right? So if we think about going across, that predicts that polonium would be smaller, but going down, that predicts that polonium would be larger. And so a valid answer to this would be, it's not possible to tell, because the two trends are opposing each other. This trend of going down, getting bigger, is much more important, much more significant. And so I would say if there's conflicting things there, I'd give the vertical trend the win. So you could say not possible to tell. And then chromium and tungsten. Chromium. Chalk in my eye. It's a hazard of this classroom. There's chromium and there's tungsten. Which one's bigger? Tungsten. The W. If we were looking at like chromium and nickel or something, we wouldn't be able to tell because there's not a very good trend across in the transition metals. But the trend does work vertically for the transition metals. Any questions? Yeah. Can I explain A again? Yeah. So tin and iodine. So here we've got tin, and here we've got iodine. And there we have the train at 7:27. Yeah, I was doing Mountain Standard Time. I don't know what time it is. I was hoping it was 7:30.
I think I said it was last time too.
I think so. So what we would expect is that iodine would be bigger because it weighs more, right? But it isn't. It's actually a little bit smaller, and that's because as we go across, those valence electrons are in the same shell. They're approximately the same distance from the nucleus, and the charge on the nucleus that those electrons see, the effective nuclear charge, gets bigger because we're adding protons without adding any core electrons. And so the stronger attraction pulls the electrons in and makes them smaller. So going across, they get smaller. Any other questions?